rectangle, so you take height times width. So the height is going to be value of a function at a certain point, I'll define all this in a second, times the width, where delta x is b minus a over n, and then you break the interval from a to b into n subintervals that all have equal width, delta x. So here we have x naught is a, x1, x2, x3, and so on. So the formula for these x values is xi is a plus I delta x. So these define the endpoints of these subintervals. But then, with each subinterval, you get a rectangle. So how do you choose the height? You actually have a little flexibility here. At this point, xi star can be any point between xi minus 1 and xi. So obviously, whatever choice you make is going to change this approximation somewhat, but now we're going to take the limit as n goes to infinity, and ends up the way you choose isn't going to matter. It's all going to converge to the same result. So you take the limit of this as the number of rectangles go to infinity. The height choice is determined by a function. You have infinitely many rectangles of infinitely small width.
That x to the I minus 1 less than equal to x, that's simply explaining why we can do circumscribed, inscribed, or midpoint?
Yes, it does.
Okay.
Yeah, so those are three of the choices.
Okay.
Yeah. And they all converge to the same result, or they should if the function actually is integrable. So the area, A, is a definite integral of f of x from a to b, which is the limit, that then goes to infinity, of this Riemann sum. Something you're probably hoping you never hear again. Tough. Okay. So by summing, so the area is actually defined to be the limit of this sum of the areas of n rectangles. Okay. All right, and then you learned that this was not the way to actually compute these things. The practical way was the fundamental theorem of calculus. Where the definite integral is big F of A minus big F of B minus big F of A, where big F prime is equal to little f. So it's an antiderivative. And of course the antiderivative is not unique, which is why some of you probably lost points from forgetting to write the plus c in your answers. All right. I should mention, if you are using Stewart, whereas in his other books, Stewart referred to the fundamental theorem of calculus as part 1 and part 2, and this is actually part 2. He decided to resolve some confusion by calling this the evaluation theorem, which, as far as I know, no one else calls it. But in the book, that's how he refers to that. So if you see him mention that, that's what that is. Okay. All right. So that's defined on a rectangle we'll call R, and this is x equals A, x equals B, y equals C, y equals D. So the function defined on this rectangle, its graph would be a surface, or patch of a surface. Okay, my corners are way off. So now, what we like to do is use integration to compute the volume of this entire shape, this solid. Okay. Now, the way that you can do that, similar to how we handled area. Whereas before we divide this interval into several subintervals, now we're going to divide this rectangle into a bunch of smaller rectangles that have dimensions delta x and delta y. And we're going to compute the volume of several boxes where the base is given by delta x and delta y. So delta x, delta y is the area of the base. And then the height, as before, is determined by the function. So now what we're going to do is have a double Riemann sum that will approximate the volume for us. So we define delta x as before, b minus a over n. Delta y is d minus c over m. So the number of subintervals in x and y are not necessarily going to be the same, although they can be. So then the volume is approximately sum from 1 to n, sum from 1 to m, because we have m times n little rectangles to account for here. So that many boxes. So the height is f of xi star, f of y and yj star, delta x, delta y. So this is the volume of one box. Okay. So we define xi and yj like we did before. So then we can define xi star and yj star in a similar way. Okay, so yj minus 1, yj star, yj. Okay, so now we're going to define the volume to be the limit as n and m both go to infinity of the sum of the volumes of all these boxes. And what we get, first we're going to define this to be delta A. So delta A is going to be the area of the base of any one of these boxes, is called a double integral over the entire rectangle R of f of xy dA. So this delta A that we have here in the approximate volume, once we take the limit, it becomes a d capital A, just as delta x goes to dx in the single variable integral. So this is the double integral of f over R, the rectangle. Okay. Now, today we're just focusing on integrating functions over rectangles. On Thursday we'll talk about integrating over more general two-dimensional regions. So we'll just start with this one.